talk in the Ecological Economics Seminar on modeling the economically optimal management of ecosystem services. Joan has her undergraduate degree from Rochester University and master's and PhD from Harvard. And she's been at Stanford for a long time now. I won't say how long exactly, but it's been quite a while. Probably one of the most influential ecologists in the country today, I would say. And she has been moving into and taking an active role in ecological economics for a number of years now. So with that, Joan. I'll stand up in the
Okay, fine. Well, thank you very much for the opportunity to speak here. As Bob mentioned, I was a graduate student in Boston, and I do remember venturing slightly north once to see the fall foliage, but honestly, this is my first time in Vermont, and it's a pleasure to be here. And I also want to acknowledge the enormous contributions that Bob has made as a founder, in effect, of ecological economics. I met him at the Bayer Institute in Sweden, must be almost 10 years ago now. So. What I have to contribute is a contribution to ecological economics from a population and community perspective. As you know, most of the leaders in ecological economics have come from a systems ecology background, and my own background is from population and community ecology, and I wish to show you that someone from this perspective as well can find a lot to do in ecological economics, and I definitely invite you into this field regardless of what area of ecology you originate in. And specifically, I'd like to talk about how a population system operates in the rocky intertidal zone of California. I'd like to tell you about the community ecology of the rocky intertidal zone in California and go from this process study to a model for the production function of, in this case, a barnacle population, and then show you how you would use a production function to calculate the optimal size of a marine reserve, and then show you that we were successful in the case of the Channel Islands of Central California in actually obtaining a marine reserve of the dimensions recommended from ecological economic modeling. So it's a throughput study, if you will, from ecology through theory and culminating in some political reality. Now, to begin then, and do I turn off the lights or do we dim the lights here? Or is this clear enough?
Hopefully it's clear enough.
Okay.
We're trying to videotape you too. And
okay, great. So this is a piece of the rocky intertidal zone in Central California. It's along the shores of Monterey Bay. And of course, it's called the intertidal zone because it's the zone between low tide and high tide. And the animals that live there are documented in this type of system diagram. Now, the hatched-in shaded area is where the rocky intertidal zone proper occurs. And to give you some background on this, when I began the work in this in the mid-'80s, the entire biology of the rocky intertidal zone was focused solely on the hatched-in area. Now, Pisaster is the name of a starfish. Balanus and Thamylus are the names of two barnacles. And there's a dynamic that occurs within the benthic part of the rocky intertidal zone that's indicated by these arrows. Balanus turns out to be able to overgrow and smother, if you will, a Thamylus. So in this sense, Balanus is the top competitor in the competition for space. And Pisaster, as a starfish, is a predator, and it preferentially eats the dominant competitor, Balanus. The reason it preferentially prefers Balanus is not coincidental. Balanus is able to be the top competitor by investing relatively little energy into shells. And so it grows very fast but has a thin shell. That enables it to be a dominant competitor because it can grow faster, but it also makes it a juicier prey item. So inherent in being a dominant competitor is an increased susceptibility to predation. And Bob Payne called Pisaster a so-called keystone predator because if it's removed, the system can culminate in a monoculture of the dominant predator. So if there's no Pisaster, Balanus proceeds to smother over and become a carpet covering the rock. But on the other hand, if you put Pisaster in the system, since it eats Balanus all the time, that opens up vacant space for Thamylus to come into the system. So in this kind of game, Pisaster is a maintainer of species diversity at the level of the prey. And for this reason, Pisaster was called a keystone species, or a keystone predator in this case. Now this was a lovely story that made its way into all the ecology textbooks of the 80s. And unfortunately, though, it turned out only to be true in special locations. The reason is that in many locations, the arrival rate of larvae is too slow to allow Balanus to ever build up to an abundance at which it could crowd out Thamylus. And what's really going on is that the intertidal zone, the intertidal community, is really the union of two halves. One half is the so-called benthic half, which is where the adults live. And the other half is the water column, which is the area shown in white surrounding the hatched-in area. And every one of these species in the rocky intertidal zone is just the adult of a species in which there's a two-stage life cycle. And there's also a larval stage. And the larvae get out into the ocean and do a whole lot out in the ocean and eventually have to get back to shore. So that the way this system operates, depends on the kinetics of the entire life cycle right here. And what happens out at this half can have every bit as much importance as what happens inside. And it turns out, as you'll see, that if this arrival rate, if this half of the circle right here closes very slowly, then you don't have enough input of Balanus into the system to enable it ever to attain a monoculture, even in the absence of predation. So if it never attains a monoculture, then it never excludes Thamylus. And so in that situation, in that situation, Pisaster no longer is a keystone predator because its presence is irrelevant to the species diversity in the prey. So what my lab was responsible for was fleshing out the nature of the coupling between the benthic half of the ecosystem and the oceanic half of the ecosystem. And so what we did a lot of work on was just what the mechanisms are that are responsible for the return of larvae to the system, since that's a major determinant of the system's kinetics. Now, I'll show you some slides now and some evidence of our major finding in this area, because we've established, I believe, that it is the relaxation of upwelling that causes larvae to close the loop right here. And the composition and dynamics of the rocky intertidal zone is determined by the relaxation events of coastal upwelling. Now, what does that mean? Now, this is a story about what gets the larvae to return. This just happens to be a picture of a larva, just to show you one, just so that we're all on the same page here. A barnacle is a crustacean, related, of course, to shrimp and lobsters and so forth. They obviously look very different as adults from shrimp and lobsters, but the larval stage of barnacles looks very similar to the larval stage of shrimp and lobsters. And this happens to be the larval stage called a nauplius. And when a barnacle goes through several molts in this stage, this is a phytoplankton feeding stage. It then ultimately turns into a non-feeding stage called a cyprid, which looks roughly like an ostracod. And then a cyprid contacts the rock, and it crawls around on the rock, and it turns a somersault. And as it turns a somersault, it then attaches to the rock with adhesive glands that are hooked onto its head. So you can think of a barnacle really as though it's a shrimp lying with its back on the rock, kicking its feet in the air and bringing in zooplankton to eat. So it's just a filter feeder having the life of Riley, you might imagine. You're just sitting there, shoveling food into your mouth continuously, and also mating with your neighbor. So it's really quite a nice life. And so at any rate, that's what a barnacle is. Now these barnacles are, as in the larval stage, are entrained out into the offshore coastal system. Now, if you just think for a moment that this is the California coast right here, really there's an entire Pacific Ocean out over here, and there is a circular current in the Pacific Ocean that goes this way, and it's called the Northern Pacific Gyre. And whenever the circular current comes near shore, it's named by whoever lives there. So when it's going upwards north of Japan, it's called the Japan current, a Kyushu current. If it comes, as it comes across and comes to California, we claim it and call it the California current. So this is the California current system as it comes down around California here. So its overall flow is southward. Now, also, there's a wind field on top of this area, which is generally circulating in the same direction, so that the wind is also blowing along the parallel to the coast here. So we have the water flowing parallel to the coast and the wind flowing parallel to the coast. Now, when the wind is blowing, it tends to push the water directly out in front of it, just like you were blowing water in your sink or something like that. It just pushes the water ahead. But here's where it gets tricky. The Earth is turning at the same time, is away from the coast. The wind is pushing it this way. The Earth is turning that way, so the water veers off to the southwest. And as the water veers off to the southwest, it creates a gap, so to speak, right next to the coast, and water comes up from below to fill the gap left by the water that's going offshore at the surface. That's called coastal upwelling. It's when water from depth comes right up next to the surface, right next to the coast. But coastal upwelling only occurs when the wind is blowing. If the wind stops blowing, then the water doesn't move offshore because there's no vector component in that direction anymore. So whether you have upwelling or not depends on whether or not the wind is blowing. And if the wind stops, the upwelling stops. Okay, now, I don't know if you can see in this graph, in this picture right here, but this is a big picture running from, basically this is the Los Angeles Basin, this is the Channel Islands here. That little nick right there is Monterey Bay, and this is going on up to Oregon and Washington. And so this is a picture of phytoplankton. Sorry about that. I don't know what I'm doing to... Oh, it's this thing. If this were California, this would, of course, be an earthquake. So get ready, Now, what's happening here is that you're seeing all of the phytoplankton offshore, and you see a little band of clear or green right next to the coast right here. That's because the water right next to the coast is cold, and the phytoplankton doesn't get a chance to bloom yet. And as the water gets farther offshore, then the phytoplankton blooms from the nutrients that have been brought up to the coast. So you get a kind of fertilizer effect along the edge here. Now, I don't know if you can see too clearly right here. If I had a pointer, I could show you. But there's actually a wider width to the upwelling zone out here. So for example, if you look here at Monterey, do you see how far it is? It's about 150 miles or so. And then as you get up to Washington and Oregon, it's narrower. And there's a gradual increase in the width of this upwelling zone as you go southwards. And that corresponds to a change in the intensity of upwelling. So I'll get back to that. There's a latitudinal gradient in how much upwelling is going on. Okay, now our finding is that, now this is a picture of sea surface temperature. And you see the blue area right next to Monterey Bay, that's cold water. And then as you get out a bit farther, you find warm water. Now this is a picture of what happens during a relaxation. When the wind stops, the water that was offshore comes into shore and collides with the rocky intertidal zone. As it comes into shore, it deposits on the shore all of the larvae that have accumulated out here. So that overall, the system works by having the larvae return to shore, like going from here to here, when the relaxation occurs. And then when the wind starts blowing again, the whole system moves back offshore, as you see in that slide over there. So now I'll show you a bunch of data slides, basically to confirm that claim. The early evidence that we had that larvae come back to shore at times of upwelling has to do with looking at the temperature and salinity record. And I should have said, so let me go back one slide, that the water that's out here is generally both hotter and also fresher than the water right up next to shore. It's hotter because, of course, it hasn't been upwelled recently, and so it's had a chance to heat up in the sun. It's also fresher because there's been freshwater runoff from the Columbia River and the other riverine sources up to the north. So this is pretty fresh water, and this is really very salty water. So you can pick up the signal of a relaxation if you see hot, salty water adjacent to the shore. And these were 4 recruitment pulses. The vertical axis is recruitment, the horizontal axis is time. And you see in the year of 1988 when recruitment occurred. And these recruitment pulses coincide with the arrival of hot, salty water adjacent to shore. So the top axis here is sea surface temperature, and you see that the temperature rises at those 4 times when the upwelling occurred, when the recruitment occurred. And also, this is a measure of saltiness. So we have fresh, did I say that wrong before? Yeah, I'm sorry. So you get fresh, hot water coming to shore when recruitment occurs. So here they have the saltiness, and then it becomes fresher and fresher and fresher. And this is superimposed upon a seasonal trend of increasing, in that case, of increasing temperature, in this case, of overall of decreasing salinity. So the next step that we did was to go directly out to sea to see if we could confirm this with on-site studies. One of our first voyages, if you will, was in fact one of the clearest. Statistically, you know that you're going to encounter an upwelling pulse if you just go out often enough. So we went out once a month for a week and took our chances. And on the 204th day of 1990, we went out one time. We hired a little fishing boat, and we went out from shore. This is calibrated from shore on that side, going offshore on this side. And then we had nets, and we were sifting larvae. And what this shows is that we hardly found any larvae at all, but we did find one of them at about 4 miles out to sea. And this was a very rough day. The captain didn't want to go because it was that rough. and we said we wouldn't pay him if he didn't go. And so he grudgingly took us out. But then the next day, the winds completely died, and the surface of the water became as smooth as a mirror. It was really phenomenal. And we repeated the same transect, and now we get 100-fold more larvae as you go out to sea. So before there were just 3, and now we're talking about 800. And so now there are all these larvae piled up next to shore, right in the middle of this relaxation. And this was the recruitment that was occurring, and this is the 206th day, which is when the recruitment of pulse was occurring. We were taking recruitment data every 2 days. And so this was a direct confirmation that the recruitment coincided with this upwelling relaxation. Does somebody know how to flip that? If somebody...
Let's flip it forward one more.
Yeah. Oh, well.
That's a lot better.
Let's just skip it. I can explain what's going on. So let me put it there and scare you with that. What we did was to introduce a kind of remote sensing called a radar, current sensing radar. So what we did was to install next to shore an antenna that fires a radio wave out over the ocean. And then the radio wave is bounced back off the ocean waves, and you look at the Doppler shift in the reflection. And the Doppler shift is caused by 2 things simultaneously. It's caused by the fact that the waves are moving, so a wave train moves. But you know from first principles in physics how fast a wave moves. And furthermore, the Doppler shift is caused by any motion in the slab of water as a whole on which the wave is located. So what you do is you take the total velocity from the Doppler shift in the echo, subtract off the component of velocity due to the motion of the wave, and you're left with a remotely sensed estimate of the current velocity. And if you do that, you get this picture up here. So this is a picture, let's see, I can just show this. This is a picture showing the southward flow, typically, of the water. Then there was a relaxation, and so you see the water coming back in the opposite direction and moving to shore. And then you find the upwelling start again when the wind starts again. And in this year, which is 1994, this is our trace of the recruitment that was going on. And this slide was taken on this day, this one from the middle one, and this one from the last one. And you see that the peak of the recruitment occurs, the recruitment is starting to really build on the day of the relaxation and actually peaks about 24 hours afterwards. So we're getting a very fine resolution here on what's going on with the recruitment. Now, it's actually peaking about 24 hours later than the peak of the relaxation. That is, it's peaking 24 hours into the resumption of upwelling because of a fact that the larvae drop in depth as they age. From collections of larvae that we took on board ship, it turns out that the young larvae of starfish, sea urchins, polychaetes, brittle stars, and so forth, all of these here crabs and barnacles. All of these larvae, when they're young, these are the names of them when they're young, drop from, in this case, 20 meters down to about 40 meters as they age. So the larvae actually change depth as they're getting older. And that positions them just to be brought into shore once the upwelling resumes. So this is a diagram. This is from work with Brian Grantham. This is what happens normally during upwelling. So water is coming from depth up to the surface and coming offshore. These little specks of barnacle larvae. Then when a relaxation occurs, the whole system comes to shore. But at this point, we see that the larvae that are old in that depth down here are down at this depth, so that when the upwelling resumes again, they're brought that last 100 meters or so. So this is getting to be a rather complete story of the mechanism that underlies the recruitment for barnacle larvae in the rocky intertidal zone. And finally, so far as this story is concerned, I'd like to mention what's happening up and down the whole Pacific coast and get back to that picture of the latitudinal gradient in California. Now this is relevant to the issue of why we're the ones to have made this discovery and why the early work of Payne and Joe Connell failed to realize the importance of the ocean. And that's because the Washington and Oregon sites that Payne was originally working at happened to be located adjacent to a section of the California current in which there isn't very much upwelling. So not much larvae are ever taken away from the intertidal zone. And so those sites happen to enjoy a very high recruitment rate all along. And so they're up here. So my hypothesis from some time ago was that as you moved progressively from Washington and Oregon down into California, you got more and more upwelling. With more and more upwelling, that more and more larvae were carried offshore. So the oceanic half of the system becomes increasingly more important in the overall story. And so the community ecology of the rocky intertidal zone down here is more dominated or controlled, if you will, by water column processes and less by biotic interactions such as predation and competition. Whereas up here where Payne was working, he has the luxury, if you will, of not having to worry about what happens in the ocean, and the entire story is just who eats whom and who beats up whom. And but that's really not the generic picture. So in the final study that my lab has done on this system, it has been in collaboration with Bruce Mengi. This is a project headed up by Sean Connolly, who's now at James Cook University in Australia. And these sites up here are Bruce's sites, and these are the sites that Sean was operating along California. And this is a picture of a latitudinal gradient right here, where we have, in this case, vacant space or free space. And you see there's a lot of vacant space in the rocky intertidal zone in California sites and not much up in Oregon. This indicates the overall low settlement rate or recruitment rate in California, which is leaving space vacant, and for which reason there are not keystone predators and so forth down here. And you see that Balanus glandula is much more abundant on the surface of the rocks up north than in California. Interestingly, because Balanus is the dominant competitor over Thamylus, you wind up getting not much Thamylus up in Washington and Oregon, and you only get Thamylus even getting into the system at, in this case, 18% cover in California when it's released, if you will, from the competition with Balanus. Meanwhile, algae, which is not sending out spores into the California current system and isn't influenced by any of these considerations, doesn't show any latitudinal trend right here. So this is basically a control that on whether this story does truly implicate the California current system. So the final information on this was a direct examination of the amount of recruitment. So this is a graph right here for Balanus, this is latitude here, with this being Washington and Oregon, this being different months of the year. And you see that regardless of the month of the year, we're getting more recruitment, a lot more recruitment in Washington and Oregon than in California. And the only change really relative to my original hypothesis is how abrupt this transition is. I had imagined that there was more of a gradual change, continuous and gradual change in recruitment from California up to Washington and Oregon, but instead there's almost a step function type jump in the vicinity of Mendocino. So even, you're familiar, if you're a systems ecologist, with the overall notion of biological systems as being earth systems, or biological systems as being coupled with the physical environment. This is a very common theme in systems ecology, and that originates, I think, in ecosystem ecology from some time ago, with the notion of the soil and the forest being one and being a joint system. But even in population biology, we really do have these coupled physical, biological processes occurring, and you can't view even a biological population as apart from the physical environment. Now, what do you do with this information? Well, one of the things you can do is to produce a something called a production function, which is something you can in turn use for policy considerations. Now, this is a graph right here of a model we made for the population dynamics of barnacles, which is going to look kind of hairy. It's got a lot of detail in it. Basically, we divided the population into two phases. Half of the population was residing in the water column, and half of the population is residing in the benthic location. And B up here, the top equation, is the rate of change of the number of barnacles in the benthic location. And that's equal to a settlement rate, which is the first term, minus a death rate. So the number of barnacles on the rocks is equal to a settlement rate minus a death rate. Fair enough. Now, out in the ocean, we have this the equation below that, which is L of xt is the number of larvae at location X out to sea. And its concentration at any one spot is determined by advection and diffusion in the water column, and mortality as well. And these two halves of the population model are coupled at the boundaries. At the boundary next to shore, the settlement rate has to balance the difference between settlement and reproduction. So that is what's coming in versus what's going out. So that is the net difference between settlement and reproduction has to balance the transport into and off of the site. So this is, on this side, fecundity minus settlement, and on this side we have advection and diffusion. Meanwhile, there's the other boundary still farther out to sea, which we're taking as a reflecting boundary. Probably can't see those equations too well, but then it's always nice to have an excuse not to look at the equation, right? So at any rate, the bottom line of this is that you can make a model for population dynamics that has a whole lot of biology in it. Now, typically, though, people just leave it at that and put this on a big computer. And that's not terribly helpful unless you want to put people to sleep. Instead, what you can do is simplify that, take that model, and approximate it by a model that you can understand. And what you can do is take advantage of scaling arguments and assume that what happens in the water column is very fast, that the water slushes back and forth at a very fast rate relative to the rate of reproduction and mortality, and assume that the water column tracks the state of the benthic stock. So if you make that substitution, you can come down with an equation, which is at the top up here, which is the rate of change of the barnacle stock as a function of the barnacle stock. Now that may sound to you like a production function, the rate of change of the stock as a function of the stock size. That's what we have up there at the top. And if you graph that, you get, or yield, the yield in stock as a function of stock size. Now I've plotted that right here, and this is the familiar hump-shaped function that you've seen in ecology courses from the logistic equation and something like that. Now what's nice about this is that if you take the population model that we have and compare it to a logistic equation, they're nearly identical. There are actually two graphs drawn here. See how this line gets a little thicker on this side? That's because there are actually two graphs, and that's where they differ. This is the best fit of a logistic equation to the process-based population model. And you actually then can use those formulas in a preceding slide to get what the equivalent value of R and K is in terms of things like advection, diffusion, and the location of the offshore front. So one can develop a very process-based model and come up with something that is appealingly simple. Now, what do you do with that? So I'd like to read. Yeah, this is always very embarrassing here. So this is from the Santa Barbara's news press, and it has to do with the setting up of a marine reserve in the Channel Islands. And this was an editorial on behalf of our recommendation. And it said, a panel of marine scientists wants preserves to cover between 30% and 50% of the sanctuary. This should be a minimum, yet some commercial fishermen want just 12% and so forth. Now, where does the supposition that a marine reserve ought to constitute 30% of the area come from? It comes from an analysis of these production functions. So here's a production function right here, very much like the one that you could derive for barnacles or anything else. As I'm sure Bob and others have told you, there are predictions from at least environmental economics about what the optimal stock size should be and what the corresponding catch should be to maintain that stock size. If the blue line right here is the production of fish as a function of the number of fish that you're leaving in the lake or in the offshore waters. And the red line right here is what you could earn if you caught those fish and sold the money and put it in a savings account. So this is the opportunity cost, what you could get from just catching the fish and banking the money and liquidating the stock. So the optimal stock size, according to economic theory, is the difference between what you could earn from harvesting fish versus what you could earn from liquidating the fish and just getting your earnings from the savings account. Now, typically in fisheries biology, one has assumed that the optimal stock size was the maximum sustainable yield, which is right here at, say, halfway over at 50. The economically optimal stock size is less than the maximum sustainable yield stock size, and is over here. And I'm going to argue, though, that a more extended consideration is that the optimal stock size is above the maximum sustainable yield at about 2/3 or 3/4 of the carrying capacity. Now, the problem with the traditional economic analysis right here is twofold. First of all, a low target stock size is, first of all, dangerous in and of itself because the stock size is therefore nearer to zero than a more conservative assessment. As importantly, the lower the stock size, the less stable the system is to perturbation. so that if you perturb it, it comes back more slowly, and that's realized as a wider variance in stock sizes over time. So a stock size down here is dangerous for both of those two reasons. And if you take into account environmental fluctuations, which in the case of barnacles, for example, would be having the front move back and forth or having the wind change, all those things that underlie, that make that production function wobble around from day to day. If you take those into account and look at at the chance of extinction of your stock as a function of the target stock size, it looks like this. That the chance of the stock going extinct is certain, is 1. If the stock size is much less than half of the carrying capacity, and it drops off to implying that the stock is really very safe once it's up here. Now, a target stock size up here isn't earning any money, though, so you're not harvesting anything to speak of up here. So you're dealing with this trade-off of how much do you harvest in order to make the money versus how much do you place the stock at risk of extinction. And a target stock size can be recalibrated into a reserve size because if you assume that you're harvesting at maximum sustainable yield throughout the area, but then you set off a certain part of the area as being unavailable for harvesting, the overall net harvest rate drops. So if some of the area is off limits to harvesting, but you can harvest at what would have been the sustainable rate outside, then you you dilute the overall harvesting level. So you'll notice in here that that a reserve size of 30% would correspond to a risk of extinction of about a quarter or so, or about 20%. So somewhere in here is where the profit is going to wind up being maximized. So if you consider the profit taking risk into account after 50 time steps, the highest profit is up here, decidedly above the traditional economic target and actually above the maximum sustainable yield. So this winds up being an economic argument for a more conservative management policy. And this is actually a risk neutral. So you don't have to value stability above and beyond what it actually purchases for you in terms of marketplace profit. Now, you could value the stability in addition, but that would only strengthen the case. So because of considerations like that, I was on the science advisory panel for the Channel Islands National Marine Sanctuary, and because of considerations like this and the increasing empirical evidence as well that marine reserves were working, we unanimously voted and so forth to have a 30% set aside. This is a graph of the Channel Islands system. These hatched-in areas are the areas that we suggested be set aside, and that amounted to 30% of the study site. And what was annoying to us is that the analysis done by the fishing industry talked only about costs to them. They made a calculation of how much money they'd lose for each one of these little spots we wanted to set aside. But they, of course, didn't take into account the rebound of the stock that would follow from reducing the fishing pressure across the board. So they really had, in my view, a bogus calculation. But that's because I feel the economic analysis was done without the level of sophistication that the ecology was done. I honestly think we brought to bear the best ecology that was out there, and it was a dynamic picture of the ecology, whereas their economic analysis was a simple static accounting at one point in time. And so I think they actually operated against their own best interest in opposing this. And we, of course, could sleep at night because we weren't taking food from their mouths. I mean, I was talking to a lot of them, and they really thought I was getting them to pay for a conservation goal. And I was saying, well, that wasn't the case, that this was going to put money into their pockets and the pockets of their children, and I could definitely sleep at night. And I might say that in terrestrial reserves, that's not quite the case. There, because it's not a harvesting issue, we are actually dealing with a different type of cost analysis. So the upshot of this is that we stuck it out and the public stuck it out, and on October 24th of last year, the California Fish and Game Commission voted 2-1 to ban both sport and commercial fishing in about 130 square miles off the state of California. And the map of the fishing, of the no-take fishing areas that they actually voted on is the same as the map that we had put forth. So I do think it's possible to go from science to policy. People frequently feel that the connection between science and policy is so tenuous and so certain to be sidetracked by political considerations that they give up on it. But I think it is possible to see it all the way through. So lastly, if you'll permit me just to conclude with a sort of philosophical type of remark. When I was a student, I mean, the question you, I'm sure, have asked yourselves is whether or not you want to buy into ecological economics at all. Are you going to sleep with the devil if you take an economic approach to conservation and to environmental goods and to environmental justice? I mean, I've had people say to me, well, then it's just like putting X's on where your heart is so that you can tell them where to shoot the arrow. And so there's a great deal of fear about this. But I don't know if we have any choice, to be honest with you. When I was a student, it was before the Berlin Wall came down during the Vietnam War. And there really was, at least in principle, a choice of economic systems that you could go to live in. You could go to Cuba if you wanted. You could go to socialist states if you didn't want to live in a capitalist society. And we used to discuss those possibilities in the counterpart of Starbucks in those days. But now we don't have that option. Just about every country is somehow capitalist to a greater or lesser degree. And it seems to me that what was appealing about socialism, which was the affirmation of goals of social justice and potentially environmental justice, the affirmation of ideals is not something that we have to lose just because we're in a capitalist society. It seems to me that the burden of our generation and of our times is to imbue economics with the idealism that we once shared in socialist philosophy. Not that I particularly was a socialist, but nonetheless it had an appeal, and the ideological vacuousness of capitalism and of marketplace methods is not something we have to live with. We can do something about that, and I hope that ecological economics is one means to that end. Thank you very much. That was 45 minutes.
Yeah.
Yeah.
Good. Thanks. These are students.
Yeah.
We have to share the microphone, actually.
Does that one not work?
I don't think, no, this is not a microphone. Why don't you take this one?
Fine.
Take this one. You guys, you can just sit here or stand.
Okay.
Pass the microphone back.
These are questions from the readings that we did before you came. So if you combine both extractive and in situ, is that right, services in one area, The target species may be more stable than if the industries were separated and the preserves fenced off. What about non-target species that may be harmed by sustainable extractive industries? One of the strongest criticisms of sustainable forestry practices is that they result in lower biodiversity. If non-target species are eliminated, especially keystone species, then the ecosystem may suffer a severe loss of biodiversity, even though it is still producing plenty of timber. Loss of biodiversity may include the extinction of species popular with tourists and therefore harm the tourist industry. How is this issue addressed by economics and target setting?
Well, certainly. Hello. Well, it's certainly addressed. I mean, you're referring to a model in which there was only one population being computed. So if you did take into account the production function from the set of species involved, then that would just be built right in. In other words, if you were valuing lots of species, including the ones being kept in by the keystone species, then there would be value accruing to the keystone species by virtue of its protection of the others as well. So the problem is simply that's a preliminary step is to work all this out for a single population and then to go on to more populations. Is that clear? Okay.
This is a question from the audience, but I can't really read the last part. So let's say,
Boy, this thing's hard.
okay. This one says, this is a question from the audience. Is there any similar studies going on in the eastern U.S.? And it says particularly Grand
Bahamas? Grand Bay?
Cluster. I don't know.
Not exactly, but there are set-aside areas off of Georges Bank, and there are some of the best studies about the impact for local fishermen of the marine reserves. We were able to show the data, which Bob Warner was able to get in a preliminary version when we were testifying in Santa Barbara. So, and there turned out to be, they put these transponders so that the GIS types could find out where all the boats were, and all the boats were lined up in around the edge of the marine protected areas to catch all the fish that were coming out, and their production went up. And so I don't know if they had at that time the kind of quantitative economic modeling that we brought to bear, but I think they were just kind of winging it a bit. But yeah, I don't know who asked the question, so I can't look at the person in the eye and ask you whether or not I answered the question you asked, but hopefully that was it.
Okay, here's another one from the audience. Can we study social systems as we do larger ecological systems? How do the principles and methods of systems ecology apply?
Well, I'm not a systems ecologist, so I can't necessarily answer that, but of course I can always have an opinion. And my feeling is that I don't see the future research on social systems as being contained within systems ecology. As you must know, some of the people in systems ecology and in ecological economics at some point have viewed systems theory as extending outwards to subsume social systems and to subsume the social sciences. I don't personally subscribe to that view. I still regard science itself and the scientific viewpoint of things as a component of society. And I would rather take social theory and subsume science into it rather than to take systems theory and subsume the social sciences into that. So I'm quite a skeptic overall on science, I must say, and I think that we as scientists need to be very careful because we are often the agents of oppression and not the progressive souls that we like to think we are. So we have to be very careful about this. And I regard this attempt to subsume the social sciences under systems ecology as aggressive and almost imperialistic. And it's reminiscent, too, of the disagreements that occurred at the time sociobiology was getting started, at which time Ed Wilson in particular was arguing that we could subsume social theory into biology. And I think that was incorrect, and it also led to enormous rancor and difficulty, which has made it quite difficult since then to try to develop a rapport between the humanities and the social sciences and science because of the aggressiveness of the original sociobiological agenda. So I don't want to make that same mistake again here in environmental systems theory either.
This is another one from the audience. How sensitive is the analysis you presented to small changes in either the production function or the opportunity cost function?
Oh, it's not. I mean, that's what it's all about, is maximizing profit when the production function is changing. So that the very risk that's being discussed right here has to do with the production function wobbling around from day to day and month to month as the wind changes. So when I showed you a picture of the production function for barnacles, for example, that was one point in time. That was like a snapshot of a production function on that day at that time. Now the next day the production function would look a little different because the winds would be different, and so the recruitment rate would be different on that day. And with the recruitment rate being different, then that would make the production function actually a little higher. And so there's still an envelope of production functions that the system experiences as the conditions change from day to day. So what you need to do then in terms of profit maximizing is to find out the target stock which will get you the highest profit with this envelope of production functions going on all the time. And now the advantage to taking a target stock which is in the stable zone is that the system is very forgiving of mistakes. The problem with the traditional target stock from economic theory, the one that's at less than half of the carrying capacity, the traditional one, is that the population is not very stable down there, and so it's not forgiving of getting the quota wrong or getting the implementation wrong or getting the execution wrong. So you buy yourself a great deal of security from your own mistakes if you take a target stock that's above the above K over 2. Yeah.
One of your articles discusses the idea of creating a true gross national product in which natural resources and other environmental aspects have monetary value. If such a system was installed, for example, if oil companies had to pay someone to drill and sell oil, who would the oil companies pay? Would they pay the government, a worldwide organization, or someone else? How could such a system be organized?
Well, that's a very sophisticated question. I don't have an answer off the top of my head to that. Certainly in the near future, I mean, unless we're going to do away with countries, the monies would be paid to the existing authorities, which would typically be national. It would be nice if they could actually be done at the state level, I must say, because if it's the state that has to bear the immediate pollution. I mean, the question involves is where does the pollution occur? The effect of burning the fuel has a global impact. The effect of the oil spills has a local impact. And so ideally, both entities should share in the cost of licensing and the benefits of licensing.
How do economists feel about subsidies for farmers? The vertical integration of the farming industry has made a very, very tough lifestyle, especially if you're a true organic farmer. What other options would an economist have for farmers? What would they suggest for organic dairy farmers of New England?
I'm afraid I don't have a clue.
Forget about the second, the New England part of the question.
Yeah, I mean, I should forget about that. I mean, what you don't want to do, of course, is to invite foreign experts, right? I mean, you know your systems better than I do. And most economists that I've spoken to are not very comfortable with subsidies to agriculture because they feel that makes them, of course, less competitive and doesn't lead to the supply of food matching the demand for food, and leads to, if anything, an oversupply in some cases. Now, the problem about the subsidies, though, is that you could take it as an independent value that you should have small farmers. And if the welfare then consists of the maintaining of the lifestyle of the small farmer, as well as what is manufactured by the farmer, then it could be economically optimal. But you'd have to go through the exercise of finding out what the economic value was to people of the existence of small farmers. Do we like having small farmers around, and how much are we willing to pay for that social environment for us to grow up in? And if one did do that, you could make an economic argument for the subsidies. But usually the economic arguments made for the subsidies is, well, usually there isn't one actually made on economic grounds. It's usually on political grounds. And so, and it's one of the funniest things about economists that I first discovered as I started going out with them is that they feel nobody listens to them. They feel that the politicians don't pay them any attention. And that's because politicians are always throwing around words like money and development and taxes and all of these tools which economists regard as very subtle instruments for social change. And I was stunned because I always thought that economists had the ears of politicians and that they could just whisper in someone's ear and get whatever they wanted. But it's business people who have the ears of politicians, not necessarily economists. And we don't, I think in one of the essays I sent out to you, we don't often draw the distinction between economists and developers, or between economists and businessmen, whereas they don't draw the distinction between ecologists and environmentalists, and they don't draw the distinction between Greenpeace and ESA, the Ecological Society of America. I mean, they think they're just the same. And so we need to have a little sharper resolution of who's on the other side of the fence sometimes, because sometimes the fence is really very, very low. And yeah.
In one of your articles, you really talk about how you are a scientist, but you kind of go out with these economists, as you just said. Do you feel like you're caught in the middle, or do you feel like you're successfully able to convince either side of a happy medium?
Well, it's still early. I mean, sometimes there are some successes. I have found it very easy to talk to economists, primarily because I do accept the possibility of economic analysis as a method to produce environmental good and social justice and environmental justice. So I don't attack the premise of their discipline. I just want to revise their discipline or add to it. Now, not everyone is that comfortable with economists. I know a number of ecological economists who really want to subvert economics and think that it's rotten to the core. If you come to an economist with that point of view, you're going to have a lot of trouble because they won't talk to you then. Now, of course, it's not clear I'm right that that one can achieve as much good with economics as I'm hopeful. So I do regard it as a hypothesis still. So I have found it easy, by and large, to talk to economists, and that they've been supportive of my work and they help get it published. The people I've had the most difficulty with have been fishery biologists and fishery economists, people actually employed in more or less bureaucratic positions in the national marine fisheries. And they're uniformly vitriolic. They, first of all, claim that it's all been done before, on the one hand, and then it hasn't. And then they'll claim that it's wrong, but it isn't. You know, and they'll go on. You know, it'll be one thing after another, and they'll often be very vitriolic in anonymous reviews. So the turf that I seem to be on and not welcome in is by fishery biologists, and potentially by wildlife biologists. I'm not sure, because these are peer groups that have their own journals and their own sociology and so forth. Now, it's not so much the economics they're bothered by, it's the fact that an academic ecologist is talking about the management of a natural resource that they're in principle responsible for. So I know that some people are trying to organize a symposium, I think at the ESA, that's coming up this summer, about the conflict between academic ecologists and fishery biologists. And I'm not a big player in that argument, and I wouldn't have actually had a symposium on that because that may just deepen the rift. But I think that's where the problem is. It's not so much the economics as such, it's the fact that ecology is becoming such a successful science, an influential science, that it's starting to intrude into wildlife management, fisheries biology, agriculture, and so on, and potentially even epidemiology and some of these other fields. So I think we need to be very diplomatic in how we go about that, and because although sometimes you get blindsided and it's too late to even do anything.
This one's kind of a specific one, and it's kind of related to fish, so it sounds like it's up your alley. A recent conference in Nova Scotia was organized to determine whether the harvestable amount of herring in the Gulf of Maine is 80,000 metric tons, as Canadian scientists determined, or 300,000 metric tons, as American scientists determined. Herring fishery regulators had to first compromise on their scientific estimates before they could examine the regulatory system for the species. How does lack of scientific knowledge about species populations and life cycles affect one's ability to set appropriate management targets? What prudent steps should a manager faced with a lack of information take, given that jobs are almost always hanging in the balance?
Wow. In that particular case, I'm not sure. I mean, it's a factor of 3. I'm not sure what that translates into in terms of yield. The overall question, though, is that's a very interesting case, the one in herring. I know that the one I studied the most were the cod off of George's Bank, and I felt that you could you could get a pretty good estimate. What I would do for herring specifically is actually look at the grounds for the two estimates and look at the science and bring in an independent and academic ecological team to evaluate it, because I'm pretty sure that the fisheries biologists don't know how to do this very well. And I'm sorry if I'm offending anyone, but I've really come to the end of my rope with fisheries biologists. And so their population estimates, I mean, we have a lot of experience in ecology and estimating natural populations, and I think that the quality of the science in fisheries biology is 20 years behind the times from the standpoint of academic ecology. And my own recommendation would be to really conduct an audit of how well they had done their science before concluding that you just couldn't tell and you had a compromise. Now, it might, of course, have been too late, because they might have already come to the table with their recommendations and you had to make a compromise on the spot. So I'm not second-guessing the political wisdom of the compromise when it took place. More generally, though, if we have this problem of how many species can you get this kind of information on, and what do you do when you don't have it, I mean, one thing, of course, is to conserve whole ecosystems and to just set aside vast tracts of ocean or coastline and just say don't go there and don't harvest anything. And that certainly is the precautionary approach, and I can't argue with that. But I'm also very critical of the claim that we can't know more. Because again, I've seen the fishery biologists waste so much money. They get a huge amount of money and find out almost nothing. And so I see them, for example, they have these boats and these ships, and they make these ships go back and forth off of California on a regular set of transects. And they pull in all these data, and then they don't analyze them. And the transects aren't scaled relative to the natural processes they're supposed to be studying. And I just see a huge amount of money being dissipated by these organizations. And then at the end of it, they say, we'll never know. Well, if we did have better academic auditing of their research programs, we might learn a great deal more than they're currently delivering. So I think it's early to say whether we've come to the limit of what we can know. And a lot of them say, well, there's this irreducible uncertainty. We'll never get there. We'll never really know how this species works, or how this ecosystem works, or how many species are in it, and so on. Well, maybe not. But the operational question is, are we at that limit? Are we anywhere near that limit? And with a higher quality of science, I think we could be closer to that limit than we are now.